Today we're going to be learning about nuclear decay, and there are three different types we'll be learning about, and we'll also be representing them with equations. So the learning targets for today, as we're talking about the atom and nuclear decay, is to be able to differentiate between the three different types of nuclear decay, as well as write the equations of alpha, beta, and gamma decay. So before I continue with these notes, I would recommend watching the video in our daily folder that says how dangerous radiation is. It is a TEDx video because we'll be kind of adding on to that video. So, and then also make sure you download the note catcher. We'll be working on that together today as well. So here we have the electromagnetic spectrum. When we hear about radiation, we might just think of radioactivity and really dangerous substances that can cause you to grow arms and legs. But really, radiation is just energy that is all around us. And most of the radiation we experience in our daily lives is what we call non-ionizing. And it is this side of the spectrum. So this is everything from radio waves, so that is how we listen to the radio, to microwaves, how we cook our food, and then infrared is the type of radiation our body emits. And then we see visible light, which is also in the non-ionizing part of the spectrum. Then going into the ionizing part of the spectrum, this is higher energy radiation, which includes ultraviolet, which the sun produces, X-rays, and gamma rays. And so this is the kind of radiation that is more dangerous. It's higher energy, and it ionizes things, causes changes in the electrons, and so that can lead to changes in your health. So the form of radiation we'll be talking about in class today is nuclear radiation, and this is the radiation released when a nucleus decays. So transmutation is the process that we are talking about, and it is a spontaneous change of an unstable nucleus into a stable nucleus. So not all nuclei are stable, and so to become stable, they decay. There are three main types of nuclear decay that we'll talk about today. There's alpha decay, where a nucleus loses an alpha particle, beta decay, where a nucleus loses a beta particle, and lastly gamma emission, where a excited nucleus will lose a gamma ray. The first kind is alpha decay. So I'm going to zoom in here on what is happening to our nucleus. So we have a large nucleus here, and highlighted is two neutrons, so they have no charge, and two protons. So this nucleus is not stable with these neutrons and protons, so it wants to get rid of them. This is what we call an alpha particle, and in the next part of this equation you can see this alpha particle leaving the parent nucleus, which creates a daughter nucleus that does not have that particle. So this particle has two neutrons and two protons. And when it leaves a more stable nucleus behind, and it also releases energy as it leaves. So we have a symbol for this alpha particle, and that's in this chart over here. The symbol is the Greek letter alpha, and then it has, just like our isotope symbols, a mass number and an atomic number. So because it has two neutrons and two protons, it's going to have a mass of 4 atomic mass units and a charge of +2. So it has 2 protons. That bottom number is going to be +2. So then if we keep going down, we see mass of 4, charge of +2. It's going to be the slowest one of these particles that is released from a nucleus, but it has a high ionizing ability. Thankfully, it has a very low penetrating power, and it can even just be stopped by paper. So if you have a paper shield, you won't get hit by any alpha particles. So we can show alpha decay using an equation, and so we're going to write out the equation for thorium-232 when it emits an alpha particle. So the first step we're going to do with thorium-232 is write out its isotope symbol. So that means it has a mass number of 232. Then if we check the periodic table, we can see that thorium has an atomic number of 90, so you can find thorium there. So thorium is going to change. It is going to become a new element because it's going to be losing 2 protons and 2 neutrons, but it will also lose this alpha particle. So I'm going to write that first. That has the mass number of 2, atomic number of 2. So since it is losing 2 protons, this bottom number is going to decrease by 2. It is now going to be 88. And then the mass number will decrease by 4 since it's losing 4 of those nuclear particles. So it'll be 228. If you check your periodic table for the element that has 88 protons, this is radium. So this will be the final equation, and you can check your work here to make sure that it makes sense. Simply add the 228 plus 4, and you can see that that is equal to 232. And then on the bottom, 88 plus 2 is going to be equal to 90. So it has the same number of subatomic particles on both sides. Try this one on your own. This is radon 222. So I'll get you started with the isotope symbol. Radon with a mass number of 222. So if we check the periodic table, we see that radon has an atomic number of 86. And then what element will it become when it loses that alpha particle? And make sure you write out that symbol for the alpha particle as well. Pause, try that on your own, add it to your sheet, and then we'll do it together. Hopefully you're able to pause, so let's do this together. First, I'm going to write in the numbers for the symbol of my alpha particle. A mass of 2 with 2 protons. So when we subtract 2 from 222, we get 218 for that number, that mass number. And if we subtract 2 from 86, we get 84. So check your periodic table, see which of these will have 84 is the atomic number, and that is polonium. So this is our final answer for that equation. Our second form of nuclear decay is called beta decay. So if we zoom in on these nuclei, here we have a parent and it has a neutron that is unstable. And so this neutron is going to release a negatively charged particle. And so this is what we call a beta particle, but it is going to be the same as an electron. So this neutron is releasing an electron. And as you can see here, it now becomes positively charged since it is losing a negative charge from it. So this beta particle is the same thing as an electron, but it's losing it from a neutron in the nucleus. So the way that we draw the symbol of the beta particle is with this B for beta, but then we will also draw that it has a mass of 0 and a charge of -1. So that's the symbol for a beta particle you will use in your equations. So because it is the same mass of an electron, it's going to be a lot smaller than 1 AMU, 1 divided by 2,000 to be exact. I have a charge of -1, and it moves fast. It also has a medium ionizing ability and a medium penetrating power, and it can be stopped by aluminum. So that is a beta particle for you. So let's try drawing the equation for this one. Let's show the equation for radium 228 emitting a beta particle. So we found radium in our last one, and it had a atomic number of 88. That was in that alpha particle example. So now what happens when it loses a beta particle? It's going to become a new element. But first, let's just write out this beta particle. 0, -1. So we know when this beta particle is released, a neutron is going to become a proton. So it's going to have 1 more positive charge than it had before. So this is actually going to increase by 1. That atomic number on the bottom will increase by 1 when a beta particle is released. Then, because that electron that is released, that beta particle, does not have a significant mass, the mass number will stay the same at 228. So now we can find on our periodic table the element with 89 for its atomic number, and that would be actium. AC, it's the first one of that bottom row, actium. And then we can check to make sure that this is accurate. If we do 89 plus -1, we get 88. That is equal to the left side. So that is correct. Now try this one on your own. This is lead 214. Find its atomic number on the periodic table, write out that isotope symbol, and show the equation. Pause now, and I'll show you it in a little bit. Hopefully you took a second to pause. Let's do this equation together. So we have lead 214 is the mass. When we find it on our periodic table, we see that it has an atomic number of 82. Then it's going to create a new element, but it's going to lose a beta particle since this is beta decay. -1 for that atomic number there. So we know it's going to gain a proton. That neutron will become a proton, will become positively charged, so it's going to be 83. That mass number is not going to change, it's going to stay 214. So we look on the periodic table, find 83, that is going to be bismuth. So bismuth is what is created in beta decay from lead. All right, here is our third and final form of nuclear decay, and this is gamma emission. So being in on these nuclei here, our parent is simply in an excited state, and so this nucleus has too much energy, it can't keep it all in, it's going to release this energy in the form of a gamma ray. So it doesn't release any particles, any neutrons or protons or electrons from the nucleus, it simply releases a gamma ray, which makes it pretty easy to write the equation for. So here is our info about gamma rays. So the symbol is going to be this gamma letter, that is a Greek letter, and we'll also have 0 and 0 here because it is not charged and it does not have a mass. And it can look different based on different fonts, but I normally write it as a Y, but just curved below. So you can write it however you choose. So as I mentioned, it doesn't have mass or charge, it's just a ray, but it moves very fast at the speed of light. To be exact, anything that doesn't have mass can move at the speed of light. And it has 0 ionizing ability, but it does have a very high penetrating power, and it can only be stopped, or it must be stopped by lead to be stopped. So that's why X-rays use lead shields. So let's do an example here for the equation. We're going to do indium 113, and so indium has an atomic number of 49, and it is going to, let's see what happens when it loses a gamma ray. So it doesn't lose any mass, it doesn't lose any charge, and so it's not going to lose anything. It's going to stay 113 and 49. It's going to stay indium, just at a lower energy. So try this one on your own. It's one of the easier ones doing gamma ray emission. Hopefully you gave that a try. Let's go at it. So we have thorium here. It's 232 for its mass. And if we check the periodic table, thorium has an atomic number of 90. It's going to be losing a gamma ray, which has no mass, no charge, and so these will stay the same. It'll still be 232 and 90, so it will still be thorium. Alright, now it's your turn. There are 7 more problems on that no-catcher sheet. Try those on your own, see if you can do those, and hopefully this was helpful to walk through creating those equations.